In the previous lesson, we learned how to describe a vector. We learned how to identify what a vector is. And then we started talking about, in section 10.2, components of vectors. In other words, taking a vector and breaking it down into components which are aligned to the horizontal and/or vertical axes. For most of the questions we did, that was usually west, south, east, north, and you would just take the vector, which could be pointing somewhere in between, and aligning its components to those axes. So what we're going to focus on in today's lesson is 10.3, which is the actual method of components. And then we're going to talk about briefly what resultant vectors are. So you actually have all the tools in the toolbox, so to speak, in terms of your math skills. The way that I'm delivering the material is consistent with the textbook. For those of you that want to add two vectors together any other way you feel like, for example, sine and cosine law, you are free to do that. So what I'm doing, I'm referring to the top of page 2 of the notes. I'll highlight this so when people come and see this later, this thing right here, okay? I'm going to just start coloring here. Why is this so important? Because I'm not forcing you to use the method of components when you're adding two vectors together. I'm well aware and agree with those that say if you have two vectors, it's probably faster to just use the sine and/or cosine law to do your business. The reason I prefer the component method for more than two vectors is because you don't want to use the sine and cosine law multiple times in terms of adding two vectors, then adding another vector. So I'm going to show you a visual explanation of the method of components on this blank slide here. So you'll see that the answer will geometrically be the same thing, but the advantage of the method of components is that you don't need the sine and/or cosine law. So here's a vector. Let's say that I wanted to take this vector and I wanted to add it to, let's just clean that up a little bit, this vector. I'm trying to draw as straight a line as possible. There we go. So how would you add those two vectors together? In your traditional training, yeah, you would do tip to tail. Based on what I was talking about briefly last week, you could take this vector. I'll just draw it at the bottom of the page here, and then take this vector. I can highlight it. Oh, it won't let me highlight it. I'll just grab it. And you do that. Notice that those vectors do not form a straight line. That's very important. Those vectors do not form a straight line. Now, if you add those vectors together, you end up with this. And that's the answer. This is the answer here, the pink vector. I want to get it really nice and good because it's super important to make comparisons later. So now I'm going to show you how the method of components will give you the same answer. What we can do is we can take the original vectors and break them up into horizontal and vertical components. That's what we did last week when we were talking about using sine and cosine and using the angle from 0 to 360. So there's the horizontal component of the first vector and the vertical component of the first vector. And I'll use a different color here because it's good to see like all the different references here. So if I take that one and then that one there, so these are right angle triangles. I am not really communicating that well there, but these are, if you draw the vectors, they form a right angle triangle. So there's a right angle triangle there and there. The two vectors here in green are equivalent to the original vector here in purple. So these two green vectors, I'm going to take them. I want you to think of them like Lego, pieces of Lego. Hey, you have a piece of Lego here. Oops. Let's take this piece over here. Don't mind the plus sign. I'll delete the plus sign after. and that last piece there. I'm going to take these pieces of Lego, so to speak, and I'm going to shuffle them around. Because when you add vectors, you can add them in whatever order you feel like. For example, I could take this vector, and as long as I go tip to tail, it's completely fair to do that. So you see what I did there? If you take those vectors, they're like a staircase. Those vectors are actually what you see down here. Isn't that cool? You see how those vectors, if you go like a little journey individually, instead of having 2 vectors, you have 4 vectors. But those 4 vectors, they tell you the same thing, don't they? Those 4 vectors, that detour of taking the components, that little zigzag, if you want, is going to get you the same answer. Let me know in the chat, does that make sense? Do you see how the green and purple vectors result in the same overall answer when you add them together? Let me know in that chat that you understand that statement. Okay. Anybody else? Or is it just 3 people? Thank you, Jai. Thank you, Sean. Thank you, Amir. Anybody else? Does that make sense to anybody else, or is it just 3 people that get that? Brian, Gianluca, thank you. There's 22 of you. I need a decent sample size here. Anyway, so what I want to do now is motivate you for why the component method is good. Because up to this point, it just looks like I'm taking one thing and I'm making it worse by just kind of breaking it up into more pieces. But here's the magical moment. This is the magical moment on why the method of components is so great. Let me take this vector here, and I'm going to play a little bit of a magician now. I'm going to move it over here. I'm going to take this vector here, and I'm going to move it down here. You see what I just did there? Do you agree with me that as long as I use all the vectors, I'm still achieving the overall goal? As long as I use all 4 vectors, I am achieving the goal of adding them together. That's very important, people, because if you look now, watch what happens when I bring this this final resultant vector up here. There you go. Can someone describe to me what this looks like? What does this shape look like? What kind of triangle is that? That's right. It's a right triangle. And the last time I checked, right triangles are the best because they're easiest to work with. Because with right angle triangles, all you need to know is Pythagorean Theorem and SOHCAHTOA. See that right angle triangle there? And that's the key. How did we achieve this right angle triangle? How did we actually achieve this right angle triangle? What we did was, firstly, we took all the x components, see that? We took all the x components and we added those together into one, if you want, super x component. And then we took all the y components, all of those guys, and we added those together into one component for that, so one super value, like the overall y component. So I'm just gonna call this thing here star. Let's go back in the math on the previous page and see if we can identify where that's located. So here's the actual method. Step 1, resolve each vector into components. So that means break it up into pieces. So if you remember here, we had these green and purple components. Those pieces represent the components. If you want, we can start to label things. So I'm going to use the letter F to represent the vector. So this is F1, and this is F2, and then this would be F1x and F1y, and this would be F2x and f2y. So in that case, what does this star represent? It represents adding up all the x's, so f1x plus f2x. And that's what you have in this table. That's what this is here. That's what star is on that page, what I call the star. It's the sum of all the x components. Similarly, you can do the same thing in the y direction. So there's our right triangle. I'm just going to get rid of the right triangle words there. This is f1y plus f2y. Again, if you add those all together, then you get one overall vector in the y direction. So what does that mean here? Well, that's what this is right here. So that's what step 2 is saying here. Add up all the components in the x and y directions. So this gives us a right angle triangle. These two steps here are what give us the overall right angle triangle. Once we have that right angle triangle, then you can go and determine the overall answer, which is this one right here. This is the final answer, this vector right here. And that vector can be reconstructed by finding two things. Its magnitude, which we can call here f, and its direction, which we can call theta. So this is the final answer, is this f and this theta. Now, I know that's probably a lot to digest in terms of the question without any numbers, but what I've done is I've prepared some tables in the notes here so we can practice this together several times. So, are there any questions before we proceed on this topic? So I'm just going to take this thing here, and I want to just get it out of the way, because this is really the centerpiece of what we're talking about today. Taking that vector, taking each of the vectors and breaking them up into pieces, and then reorganizing those pieces, adding up the x components, and then adding up the y components separately to generate an overall right angle triangle. We're going to go through this process. I have it here about 8 times, I think. But there's 3 major examples that I start with, and then I start to diminish the number of steps by using less vectors. So here we go. Here's our first example. We're going to add 3 vectors together. These vectors are called displacement vectors. I mentioned last week that you do not need to be an expert on physics today, or necessarily in this course. I will explain to you what displacement is in the next week's class, after we have a break week, of course. So what is displacement here? It's just a vector as far as you're concerned. And here are the actual quantities we're adding together. We're going to take 3 displacement vectors, and we're going to add them together by using the method of components. So this first displacement vector is going to go in this box here. Now, this table here is not a table that's from the textbook. This is just me making a visual aid for helping you to study. So if I just take these vectors here, you can transcribe them into those areas if you like. I'm not going to copy and paste them like this in the next example. I'm doing this the first time just so you understand where things fit. So there's the second vector. And then the third vector, of course. So what did we do last week? Recall that we did components of vectors using angles between 0 and 360. So what I have here, these quantities are not in the most useful way in terms of finding components. So we need to figure out what the angle is between 0 and 360. So let me know in the chat, what angle is 25 degrees east of south? What angle is that between 0 and 360? Sorry, east of north I meant to say. East of north is 65. Jai, that's correct. How did you get that angle? Can you explain in the chat for people that are not sure? Thank you. It's 90 minus 25. For those that are a little bit unsure about what's happening today, what we did last time is we talked about how north, east, west, and south can be represented by angles between 0 and 360. So this is 0 degrees, and just like you did in high school, if this is 0 degrees along the x-axis, so to speak, you go counterclockwise and you go round and around. So north is 90, west is 180, south is 270, and east is 0 or 360, depending on how you want to use it. I'll just use 0 here. So what we have in the first example, which is 892, 25 degrees east of north, is really just two numbers. And those two numbers that you need to have here are the magnitude, which is 892 meters, and the direction, which is 65 degrees. Now, what would be the next one? So the next one's 274 meters. And what is south? What angle is south? Well, I've mentioned south already as 270. Okay, your turn. Can someone tell me in the chat what 28 degrees north of east is? Yeah, it's just 28. So a nice and easy one to finish there. So there you go. We have all the numbers that we need to create the components. So remember, each of these vectors can be a little triangle on the side. Each of these vectors here, which has a magnitude and a direction, can be written as a triangle. Let's just move that out of the way. So for example, this 892 is over here somewhere because it's 65 degrees. See, 65 from here. So that's that first vector. The second vector is pure south, just south. And then the third vector is also somehow like this. And those things here that I'm drawing are the components. I'm going to take the components and highlight them. Maybe with a finer highlighter. So this is a component, this is a component, this is a component, that's a component. And the south one is kind of funny because it only has the vertical component. So the things that I've highlighted in yellow represent components, and the quantities or the vectors that I highlight in blue represent the original. So that's why the middle one, the original, is also equal to the component because it's only in one direction, basically south. It's not a mixture of like south and west or something. We talked about how you actually find the components using the formulas earlier on in the booklet. So I'm just going to remind you what that formula was for a second. I'm scrolling through 3 documents at the same time here. So here is the actual formula, which is getting the components. Maybe I'll just write it over here. When you want to find the x component and the y component, you want to take the hypotenuse, which is 892, and multiply by cos 65. So I've done these calculations already, so I'm just going to just drop them from the from my solution file because they're probably too small to write in the boxes. So there's the solution for the, not the solution, but here are the x and y components. Just take a second and see the calculation there. I did 892, and then I multiplied by cos 65 because the x component is always going to be the value of the hypotenuse, or in this case, the magnitude of the vector, 892, and it's always going to be cos of the angle in standard position. So what I did in this box here, and the second box, and these two boxes here, this represents an example like last week. So what we're doing here is exactly what we did last week. And I'm going to show you my solution file quickly to remind you about what we did last week there. Remember last week we took a vector like that, and then we would do the angle in standard position, and then we found the x and the y components. You were very exceptional at doing this last week. I was very impressed with your performance on this last week. And what I'm doing here in this table, each of these rows is really like one of those examples. Each of these rows that I'm showing you here is exactly one example from last week. So this question's like triple the work, but triple the same work. If we take a look here, the x component is positive in the east direction. So this 376.98, it's facing east. And this 808.43 is in the y direction. If it's positive, it represents north. So what we have is the original vector, which is kind of pointing in the northeast direction. It's going to contain easterly and northerly components. You see that? The answers are positive here, so they're facing in the correct directions. Can someone discuss with me here the second one? This one here, the second one is facing south. If it's facing south, would you expect it to have an east or west value to it? Does this vector here, south, have any east or west component involved? No. Yeah, not applicable. Thank you, Jai. So the x component here, like you do not need math. You do not need to do calculations here. This is 0. And this answer here, it's south, so it's negative 274. Like you do not have to do a calculation there. But I want you to just humor me, because what I'm going to do now is show you the answer by using these numbers here. So I'm going to do if you did 274 cos of 270, do you still get 0? You actually do. You can check it on your calculator. 274 cos 270, that angle in standard position, is actually 0. So whether or not you were observant to the fact that this thing is not going to have an answer in the east direction, it's going to be 0, you still get 0 regardless of if you saw that or not. So that's a very useful thing to know. Similarly here, if you calculate or evaluate 274 sine of 270, you will get negative 274. So everything is working out very smooth here. See that? We still get the quantity that we needed. We still get negative answer of 274. So where are we in the process right now? In terms of the method of components, we're just breaking up the vectors. We've done 2 of them so far, and we've found the x and y components. In general, there will be n vectors. In this case, there's 3 vectors. So if this question was only to add 2 vectors by components, it's very similar to the visual description that I started off today's lesson with. Now for the last row, we're going to do the exact same calculations. So what I'd like someone to do in the chat, or many of you to do in the chat, is to tell me what the x and the y components are here. So what is the x component and the y component of the third displacement vector? So if I take 285 cos 28, Yeah, 251. It's okay, Jai. I think you're a step ahead. You're a step ahead of us, Jai. That's cool. Yeah, you showed the sum. So thank you, Anthony. And 133. Yeah, we're good, Anthony. I did these on a computer program. Like I wrote my little, I have a little program that I used to do these. So I might have a little bit different accuracy than you. Nothing wrong with your answer. I think I'm keeping a little bit more accuracy than you. That's all. So anyway, you get those quantities. So let's see here. We have a positive value and a positive value. In the x direction, when it's positive, that means it faces east. And that makes sense because the question, the third vector, is facing in an easterly direction as well as a northerly direction. So that's good. And the second answer here, the second or y component, is positive because it is facing in the north direction. So everything is making sense here in terms of the components' signs, like positive or negative. So what we have done here now is we've taken the original three vectors and we've broken it up into pieces. And here are the pieces. The components represent the Lego pieces, what I was talking about earlier. So over here, these vectors here, these green vectors and these purple vectors are the components or the building blocks. And that's what we have in this table, is these little building blocks. But instead of adding them in this way by doing one vector at a time, we're going to take all the x components and find a total for those. And then we're going to take all the y components and we're going to find a total for those. So that's what I'm going to ask you to do now. So Jai's actually calculated the first one. You're going to add these up. You're going to just add up those components. And don't worry about the units here. As long as your answer has the units correct, I don't care about the intermediate steps having units. When I added these up here, I also did get 628.62. A little bit different than Jai, a little bit less on the accuracy, but if you're in that, if you got the first three digits right, that's okay. And the other vectors, if you add them up, the y components give us a total of 668.23. So what is this saying overall? It's saying that these three vectors here are equivalent in terms of their sum to these two vectors. So these two vectors down here have the same sum as the original three. Adding these three together is not fun. That's supposed to be a sad face. Adding these two vectors together is fantastic because it's a right angle triangle. When you draw these vectors together, you get a right angle triangle. So now we're on to the process of actually reconstructing the vectors to find the resultant. So the resultant is really just the sum. So what you're going to do now is you're going to take these two vectors here and you're going to draw them and rebuild the overall vector sum. It doesn't matter which one you start first. I'm going to start with the first one here, which is 628. And I'm just going to draw it that way. Because, why am I drawing it to the right? Can someone let me know in the chat, why am I drawing it to the right? Because it's east. Thank you. And which way should I draw this one? Should I draw it up or down? Should I draw this one up or down? Thank you, Sean. By up, I mean north, but I'm just talking about on a paper, like how to communicate it. So that's why this one's drawn in this direction. Remember that there is a north and an east here happening. And why are they north and east? Because that's positive and that's positive. So if either of those were negative, it would point to the left or down. So those vectors represent the vector sum that is equivalent to the vector sum of the original question. I can connect them together and draw a hypotenuse, and I'm going to just call this delta D. I'm not going to call it F because F here is just an example of a name for a vector, like a variable. In our question, we're adding up things that look like delta D, which are called displacements. So I'm going to call that delta D, but I also need theta. Whenever you're drawing the diagram with the vector, if you don't put the arrow here, it's okay for me because it's just the magnitude anyway. Some people are really picky. They want you to write this as a magnitude, and I think that's good as well, of course. But I'm not going to pick on you too much because you're rookies here for the most part. So what you want to do now is find delta D and theta. How would you find delta D? What right angle triangle mathematics would you use to find delta D? How would you find delta D? Very good, Jai. And how would you find theta? Yep. So use the Pythagorean theorem and inverse tangent. So that's the way that you finish off the question. So I've already done the calculations here, and because you're very, very capable of using Pythagorean and tan, I'm only going to screenshot my answer there if you don't mind. So because that stuff there won't fit by hand nicely. So what I've done now is I've reconstructed by using the Pythagorean theorem. So that's the first part here. I put a subscript delta D total. Perhaps I should put total here as well, to be fair. Whoops. So delta D total. And also, I used inverse tan, and I got 46.7 degrees. So we're so close to the answer now. The last part of the question comes down to communication. When I'm evaluating these kinds of questions on a test, we're at the mercy, for the most part, of the textbook. What I mean is that the textbook will ask you to fill in the blanks a certain way. And in terms of like when I'm testing you with the MyLab software. So what I'm showing you here, what I am showing you here is probably more strict than the textbook. So if you're able to do it the way that I'm showing you, I'm more strict than the textbook. So you should be just fine when you're doing evaluations on this topic. So the final answer here, delta D total is a vector. Now, how do we present the vector? It's actually the expectation is in the question. So you see how in the question I have a magnitude and then square brackets with a direction? Well, that's what you do. Give the answer the same way that I gave you the question. So if you're like, I don't know how to present it, well, just look at the question and use a similar style. So 917 meters. And then here we have 46.7 degrees. So this is 46.7 degrees. So we could say here 46.7 degrees north of east, which is how you would probably see it in the book. But you could also write it as east 46.7 degrees north. Either of these answers, both of these answers are equivalent, and I don't care which way you write it. For the sake of our notes, though, I usually write it the first way just because I'm not trying to confuse people by flip-flopping. So there you go. We spent a lot of time on one example. I realized that. But it's important that I went really slowly with this first one. So now you can actually go and complete the entire booklet. Everything else that you see in the booklet is just more and more of the same. So what I'm going to do is one more example, but this time, with all respect to you, we're going to do it at a much faster pace. And then, so we'll do this example here together. I'll leave this one for you to try on your own. And then we're going to do some questions after the break where I try to take the process and streamline it. So what you have in the future examples here, you see how it's kind of a smaller table? What I'm doing here is really just streamlining the heck out of it. So let's do one more example fully, top to bottom, and then we'll take a short break. And then we'll continue with kind of more of a rapid fire express version of doing these questions. And of course, in your third hour at 10 o'clock, there is an assignment which you can find on MyLab. as per usual. So, help me out, people. It's time to pick up the pace here. What is the, what we need to take these directions here and write them as angles between 0 and 360. So while you're pondering that, I'm going to just write down the magnitudes because those are necessary. So can someone give me the direction for the first one? What is 17 degrees west of north? What angle is that between 0 and 360? Thank you, Anthony. In the chat, Anthony, can you let your classmates know what calculation you use to find that? And that goes for anybody else that answers. Thank you, Anthony. 90 plus, right? Yep. Okay. How about 23 degrees south of east? What's the answer for that? Can someone else do that one? Thank you, Gianluca. And can you show a calculation of how you got that? Perfect. The third one, 73 south of west. That's hard to say, sorry. I'm like slobbering here, south of west. Geez. Anyway, what's the angle for that one? Anthony, how did you get that? What was your calculation? All right, and anybody else on the last one? Someone new? Anybody new that wants to throw a number in there?
35.
35 is good. Thank you, Anthony. And I won't ask you to write it. You can write it in the chat if you don't mind. But how did you get? You can just say it out loud too if you want.
90 minus 55.
Thank you. And Anthony, number 2 or number 1. I don't know who's number 1 or number 2. We'll call you 1A and 1B, like the Leafs power play or something. So yes. And I can't even say Anthony C because you're both Anthony C. So Anthony squared. Anyway, those are the magnitudes and the directions. Now we can go and get the components. So remember, to get the components, you're going to use cos here, and you're going to use sine here. So I'll show you the calculations for those. I'm going to actually just copy and paste this part. So if you don't mind, this one here, writing it by hand, is probably going to waste more time than we have at this point. I think I went a little bit too slow on the first one, but I hope that it was worth the investment. That's good enough. So you see here, I did cos of 107, sine of 107, cos of 337, sine of 337. Let's take a look at some of these signs. I really want you to understand the ones with the negative signs. So I'm going to take the first one here, west of north, okay? Now, when you find the components, you expect the x component to point west. And what do you see? You see a negative sign. So that means it's the opposite of east, so it's west. And then this one is north, so that's consistent. The next one's south of east. So there's east, and there's a negative answer pointing south. You can do the same thing over and over again. I'll just do the next one here. South of west, so we have to the left or to the west. And we also have, I'm trying to get that negative sign, there we go. And we also have negative here, which is south. So you see how the components remained consistent with the original directions. And of course, the last one's just east and north, and we see a positive and a positive there, so everything's good. So if this was a little bit quick for some people, for those that weren't here last week, potentially if anybody wasn't here last week or didn't watch the video of it later, each of these check marks, each of these rows was an example last week. So we're doing 4 examples now, at the pace of what we did one example with last week. Don't be too alarmed, because really it comes down to identifying the angle. The key to doing this table is finding the angle. Once you have that angle, then it's punching numbers on a calculator or using a spreadsheet or whatever the heck you like to use. So we're at the end of the component part. We're going to take those components now and add them together to find the total in the x and the total in the y direction. So what do you get when you add these numbers together? I'll just write the answer here. You get 714.94 meters. And in the y direction, you get 212.82. So these questions, I made these questions up. I was a little disappointed with myself in terms of this one also being positive and positive. What that means is that it's going to face to the east and to the north. So I don't want you to think that every time you get an answer, it's always positive and positive. It could be negative. Like, you could have all kinds of situations. So I don't want you to think it's always positive. So my apologies that this one's also positive. On the other hand, though, I can recycle the diagram from the previous question, which is what I'm going to do right now. So it actually has the same diagram as the previous question, except with different numbers, of course. So there's the x component, and there's the y component. And what we're going to do now is reconstruct to find the displacement, the overall displacement. So to do that, we're going to use the Pythagorean Theorem and inverse tangent. So here's the following calculation. Just getting that oops. There we go. My computer was misbehaving for a second. I was going to give it detention. Anyway, so the first step here is to use the Pythagorean theorem to find the hypotenuse, which represents the magnitude of the resulting vector or the resultant vector, or if you want, the sum. So the hypotenuse represents the final answer, the magnitude of the vector. And then the angle, theta, over here, measured north of east, is going to be found by using inverse tangent. So if you're a little bit weak on your SOHCAHTOA, you need to know SOHCAHTOA here. I know we covered it last semester, and you obviously know it from high school, but this is something that I'm not going to go back and remind you about. If anybody's like rusty, okay, Anthony, yes. If you're going to use the method of components, it will always be a right angle triangle in the worst case. Okay? You will only need to know right angle triangles if you use component method. That's the advantage of component method. Yeah, so then you always use tan at the end. This is how it works, okay? If you want to use components, it's always going to be sine and cos, and then you're going to finish off with Pythagorean and tan, always, if you're going to use components. If you don't want to use components, which I'm not teaching here, then you're going to use sine law and cosine law in general. As we get to more examples in the next booklet where we do application questions, I'm going to do examples where I use components, and I'll do examples where I use sine and cosine law, just because there are people here that want to use sine and cosine law. But in terms of automation, you can see that this way with components is far more easier to automate. So here's the final answer. Once you piece together the magnitude of 746 meters and the direction here in this case of 16.6 degrees north, because it's rotating to the north relative to the east axis. So 16.6 degrees north of east. Okay, that's probably the worst of it. I don't plan on you 4 vectors on the test, at least not pathologically every question. And I haven't set up your second test yet. I mentioned to everybody that your second test, I haven't set it up yet. But when I do set it up, it's most likely all going to be on MyLab, or there might be a portion of it that I do through Blackboard and a portion that I do through MyLab. But we haven't crossed that bridge yet, so I still have a few weeks to decide how best to generate the test for your benefit. The only issues I'm having in terms of setting up a test, the challenges that I face, are how to best set up the test to really fairly gauge you as a class and to do it in a way that's meaningful. We left off with example 27, and I mentioned that you can try this on your own. For those that have tried it, I will post the solutions to the booklet at the end of class, and specifically I'll post them as you're writing your in-class assignment. So probably at just after 10 o'clock. In the meantime, though, I'd like to move on and practice some more questions, just in a more compact way, so without as much writing, hopefully. Because it does seem like a lot of writing to do. Maybe we can streamline that. We're going to actually go to question 28 now, and let's see how this works out here. So this table here is just something that I've created that streamlines the process that you saw in the previous pages. In this question, it's a bit ridiculous to use components to add this question, these vectors together in this question, because this one faces north and that one faces east. And I think you would agree with me that that's very easy to do. You see, you can just draw east like that, and then you can draw north, or vice versa. It doesn't matter which one you draw first. And then there's your answer. There's the resulting vector. So how would you find that vector? You would do Pythagorean and tan. So over here, you would use 37 squared plus 25 squared. And the angle would be tan inverse of 25 out of 37, giving us answers of 44.7 newtons and 34 degrees. So this question, you don't need a table to solve things. The final answer would be 44.7 newtons. But what if you did decide to use the table? What if you're like, no, would the table work? If I fill this table in, would it still work? Of course it'll work. That's why the table's so valuable for the tougher questions. Let's try this here. 25, 37. North. What direction is that? What angle is that? 90. And then east is 0. So if you did 25 cos 90, you're going to get 0. And if you do 25 sine 90, you'll get 25. 37 cos 0, 37 sine 0. And if you add those together, you still get that. You see how the table still conforms to the method? So obviously here, this stuff in pink here, you don't have to do this table. It's ridiculous because the vectors are so easy. But hopefully you can see how valuable such a table or a setup would be for more general cases where you have stranger things happening. Look at that. West of north and north of east. So let's see if we can figure out to fill this table together. So I'm just going to scroll it down here and we'll slow it down for this question. So let's fill this table in. This is 700 and this is 900. Those are the magnitudes. What is this angle between 0 and 360? 166. Can you tell the class how you got that? Thank you, Jai. All right, somebody else. What's 19 degrees north of east? How do you write that as an angle between 0 and 360? Thank you, Anthony. Thank you, Ethan. Welcome to the party. All right. So there you go. So in these boxes here, remember the first one is equal to Fi cos theta, and the second one is equal to Fi sine theta. Reminding you of how it works, okay? So if you do 700 cos 166 and 700 sine 166, you'll get those two boxes. I'm going to copy and paste those boxes right now. The x component of the first vector is negative. Why the heck is it negative? Why is this vector negative? Because it's west. And why is this vector positive? Because it's north. The same reason that this one's positive. And this last one here is going to be an x component of positive because it's in the east. Are there any questions about these calculations? Let me know in the chat. Do you find these calculations easy to do? Or do you need more clarification? Please let me know in the chat. Thank you, people. It's important that you realize what we're doing here is just mechanical. I'm not doing application with you today. So it's really important that you get the mechanics of this down, so when we do application questions later in the next booklet, you'll be very aware of how to perform those calculations. So how do we get this vector, the magnitude of the resultant vector? Let's draw a picture here. So we have these two vectors here, which are the total of the x and the total of the y. So this is 171.760, and this is 462.357. So if we take those vectors together and add them, that's the vector here that I'm talking about, f, the resultant, and that's the angle theta. So in this case, the Pythagorean theorem and tan. Again, as per usual, Pythagorean theorem and tan. So let's get those calculations on paper, or at least on the screen. So there's the calculations. So I did the Pythagorean theorem here using the horizontal and vertical component sums to get 493 pounds of force. Now that's the magnitude. We need a direction. The direction is obtained by finding theta using inverse tangent. So once we get theta, which is 69.6, again, this question is a north of east answer. So it's very, very misleading on my part to every single question's been north of east. I promise you, the next question will be different. We will have an answer that does not face north and east in some combination. So hopefully I can convince you of that with the next example. There's 4 questions left. perhaps what I'll do is I'll put one up, we'll do it together, and then I'll give you the second one and give you time, maybe 10 minutes to try it on your own. I'll be here with you silently as I fill the answers in for the second one. Does anybody need more time with this question? So here's a question that almost certainly you can tell is not going to face north. How am I so keen to know that? Well, both of the vectors originally, which are force vectors, they're facing in a direction east of south and west of south. So that means that the final answer almost certainly is going to have south in it. I'm not sure if east or west is going to be the horizontal component. It depends on individually how these vectors compete with each other in the east and west directions. But in the meantime, we don't have to worry about that because the math never lies. We can just do the calculations. So let's set it up here. So we first have the original vector. This pencil needs to, that's a little bit better. So we have 1250 and 1370. These are the components, the magnitudes of the original vectors. Now, east of south, what angle is that between 0 and 360? Let's go through this one a bit more with a diagram. So here's south and here's east. So we're somewhere over here. So that's 334. Thank you, Anthony. See, this angle here is 64 degrees. But remember, south is 270. So it's 270 plus 64. So that's how you get 334. And you can do a similar calculation with the other one here, west of south. I'll do that one down here. So that's over here. That's 22 degrees west of south. It's funny. I'm trying to go really slow with my stylus here, and it's like I'm in a race here with a turtle or something. Anyway, so what angle is that between 0 and 360? That's correct, Jai. So I do 270 minus 22. So that's 248. So to find the components, we're going to use cos and sine here. So remember, for the x component, it's going to equal fi cos theta. And for the y component, it's going to equal fi sine theta. So in this case, the x and y components, you're going to get some positive and negative numbers depending on if it's facing east or west, and for sure facing south in terms of the vertical component. So there you have it. So what I did was these numbers here, 1123 and negative 547. So if you do 1250 cos 334, you get the x component, and 1250 sine 334 degrees, you get the y component. And indeed, as we speculated, the x and y components are aligned correctly with west and south and east. So let's take a look here individually. So this east here manifests itself as a positive right there. And then we have south for both of them. That's why these answers are both negative. And finally, you have a west over here, which is this negative number of 513 pounds. So there you have it. You can see that the components are consistent with the original vector. And the reason that we get away with all of it, the reason that it works out so nicely, is because we're using the angles in standard position, and we're taking advantage of the property of sine and cosine in terms of their signs, their plus and minus values in the four quadrants. Okay. So eventually, you get those two quantities for the x direction, you can add them together, and the same thing for the y direction to get those totals. That allows us to draw a triangle. So let's do the triangle here. And notice that it's not east and north anymore. Thank goodness, because hopefully that was kind of getting a little bit irritating that they're all the same. This vector is going to be over here, and that component is 610.282. And then this one here is facing negative. So negative means it's going south. So I'm going to draw the vector down here. It's not the scale. Now, I didn't put a negative sign here because when I write these quantities, these numbers in black here, I'm just referring to their magnitudes without the actual plus or minus signs. So we're going to find out this angle and that force magnitude like that. To find those quantities, you do what you did before. You do Pythagorean and tan. So F here, via the Pythagorean theorem, is going to be 1920 pounds. It's a little glitchy today. There we go. And then the direction, I shouldn't say the direction, but the angle theta is 71.4 degrees. So what is the resultant vector? The final answer. Our final answer is right here. Our final answer is going to be 1920 pounds, but the direction is a little bit dangerous. You got to be careful with how to write it. Don't forget that there's an axis here, and that's north, and that's east, and that's south. So this direction here is south of east. That's what I'm trying to say here. South of east. And the angle is still 71.4. So it's important that you take the angle that you find using Pythagorean and tan, the angle that you find using inverse tan, and you write it in the context of the physical space that you're working with, which in this case is east and south. So that's the worst of it. We've now gone through 4 examples fully where we've had to deal with directions that are not aligned to the axes. We had a 5th example, which was super easy, the one involving just north and east. But at this point, I feel comfortable to leave you to try one of these on your own. So maybe if you have the patience to do that now, we'll go through question 31. What I'll do is we're going to figure out the angle together for each of them. And then once you have these angles here, once you have these 3 angles, you should be good to go in terms of filling in the table and completing the method. So let's get those quantities down. So I'm just going to write down the obvious, 14.4, 26.5, and 18.3. What I'm relying on you now, just for the next minute or two, or less even, give me the angles, please, for each of those. And then from there, I'm going to give you 5 minutes, and I want you to reconstruct and do everything yourself. See how far you get on your own. So 15 degrees north of east, what angle is that? What angle between 0 and 360? What angle is 15 degrees north of east? Yeah, it's just 15. And what angle is 45 west of north? Someone else? Oh, thank you, Jai. It's okay. You're doing well. I mean, I want to see more people to make sure they're okay. I appreciate it. Okay, someone I haven't seen in a while in the chat. 28 south of east. Sorry, this is 135. My apologies. Anybody else in the chat? What is the angle for the last one here between 0 and 360? 28 degrees south of east. I'm going to draw it, Joshua. So here's east. Sorry. Here's east, and here's 28. So what angle is this? What's this angle here? Or how do you calculate it? Thank you, Nikita. I think Josh, you wrote it as from north. And if it was from north, it would have been better. It's okay. Thank you though. I'm just waiting for PowerPoint to behave. So that's 360. It's all good. Every answer that I see in the chat is important because it gives me insight into where everybody is with the material. So there's 332. If anybody is like, if this stuff here is bugging you and you're like, I don't know how to get those angles, but I know how to do everything else. Like if you're good with everything else, it's just these angles, then you probably missed class last week. That's the only thing I can think of because we went through a ton of these last week, and I really took my time with everybody to make sure they could do them. Okay. What I want you to do now, it's 9:27. I want you to take 5 minutes on your own, and I want you to fill everything else in. I want this, and I want the entire table filled in. So I'm going to stick around here with you. I'm just going to not talk. So you have 5 minutes, okay? Okay, so eventually you should get to those components totals, which are 11.329 and 13.874. These are in units of kilonewtons, which is a unit of force. You don't have to know to describe units of force yet, but it's nice to know what those quantities sound like in English. So I'll finish off here by just pasting out the solution, the reconstruction process. So there you have it. I don't think that it's too much of an ask for you to fill this table out, maybe in the span of 5 or 10 minutes tops. Now the thing is that when you do a test, you won't necessarily have a table like this to fill. This table is something that I created to help me do components more efficient. So for you, if you want to use such a device, it's up to you to remember how to draw such a table. It doesn't have to have all the bells and whistles that I have here. The main thing is that you want to have the number of rows, 3 rows for each of the vectors, and then you want to have the 2 columns for the components. The biggest thing that you're taking away from this table, the most critical thing that you need is this. This is the heart of the table, the yellow stuff, okay? All the other stuff is fluff. You don't have to write all that stuff down. You don't have to write down these calculations. Like, I don't care about those. The most critical numbers that you need to do these questions are the ones in yellow. That's the stuff that you need. That's the stuff that is not negotiable. Because if you don't have that, then you can't proceed with the calculations. And furthermore, you can't go back and check your work. There you go. Because let's say you didn't write these down here. Let's say you just didn't write those down. Then if you have this number here and it's wrong, you have no way of tracing it back. So that's why it's important to put some extra stuff, extra calculations. So there are 2 more examples in the book, plus the big one that I skipped earlier. We skipped the big one here before, and I said you could try it during the break earlier, or you could try it for homework. I'll leave that for you to, like I said, I'll put the answers on Blackboard. I plan on doing one more of these with you in class. Just waiting for PowerPoint to do its thing. So there's one with 2 vectors, and there's one with 3 vectors. Your choice. Do you want to do 32 or 33? Your choice. 33? Okay, yeah. All right. 33 does have more workload, but I really want you to, if there's people in this audience that are like 32 and 33, same thing. It's just the one has the extra vector. If you're kind of like whatever, I don't care, it doesn't really matter. That's probably a good frame of mind to be in, because it doesn't matter that there's an extra vector. The extra vector doesn't really make a big deal, but we will definitely do 33 together as per your request. So the first thing that you want to do here is write down the magnitudes. So that's easy. I'll just dump those in here, 75, 80, and 85. Remember, this table is my table, my little creation. So if you do use it, you need to draw it yourself in general. Okay, now take these angles here. 42 north of west. What's that? Well, it's over here somewhere. That's this angle. But we don't want that angle. We want the angle measured from the x-axis. So that's over here. So that's 180 minus 42. So that's 138. And then the second one, 63 south of east. So that's over here. That's 63. But you want to go the other way because you want to measure it from 0 degrees. So that's 360 minus 63, or 297. And finally, we have one more, which we haven't seen one of these today. This is nice. Actually, no, we saw one earlier. Never mind. 37 east of south. So that's 37 there. But you don't want that angle by itself. You want to measure the angle from over here all the way around. So that would be 270 plus 37, which is 307. So at this point, it's a matter of just using the sine and cosine to find components. So this will be Fi cos of the angle theta, and then this will be Fi sine of theta. This table, my motivation for this table, for using it, the subscripts just as Fi and theta I and Fix, is because I'm trying to make it look as close as possible to what we see here. You see how the subscripts are here? I'm using the notation as identically as possible to that notation there. So that's the motivation for that. Excuse me. So we can find the x and y components. All right, anybody have the first two? What do you have for the first two components? What goes in this box here? Yep, and the y component, Sean? That's correct. I'll fill those in a second. The next one, can someone give the next row? What goes here and here? Two numbers. Yep. And that's right. Can someone else give the numbers for these two entries here? So far, these four numbers are what's in the chat. Thank you, Sean, for that. Anybody else have a couple of numbers for these boxes? Thank you, Gianluca. Yes. And the other number? Yep. So those numbers are all good. Everything's looking very, very smooth right now. So let's just put the, I have them typed up here. I didn't want to write them by hand. Plus, I wanted to show you extra decimals for those that had extra decimals in their answers. Good enough. So you can see here that the components, when you add them together, you have east and you have south. So if you take these two quantities here, the sum of the x and the sum of the y components, the diagram looks something like this. It's going to be 31.738 this way. And then this is not to scale. That's going to be 88.980. Which, when you add these together, produces the resultant force, which is F, and the angle theta. So, if you use the Pythagorean theorem and inverse tangent, you will get theta and you will get F. And that allows us to finally write down the resultant vector, which in this case is going to face, we'll discuss the direction in a second, but the answer is this. It's 94.5 kilonewtons. And then you have 70.4 degrees south of east. As you know, there is an in-class assignment today. It's on my lab, and it'll be open at 10 o'clock. For those that want to take a break until 10 o'clock, you are free to do that. For those that want to stick around, I'll take the extra time and I'll go back and do example number 32. So I'll go back and do 32 at this point. It's your choice if you want to stick around to see it. Does anybody need more time with this question? Okay, I'll just wait for another 30 seconds and then I'll go and dip back to 32. Another question involving adding two forces together, finding the resultant of two forces. So we have the first force, which is 15,000 pounds. And the second force, which is 26,000 pounds. Now, without saying a direction, that's not a force, it's the magnitude of the force. So I should mention here that we need to apply a direction. So in this case, we have south of west. So that's like over here. And then the other one is west of south, which is over here. Each of those will be measured from the x-axis, the positive x-axis, as a standard angle between 0 and 360. So the first angle here is going to be 180 plus 23, so 203. And the second angle will be 270 minus 35, which is 235. Once you have those angles, you've unlocked this table. Like, this table is done. As far as you're concerned, you're just punching numbers on a calculator now. So using the sine and cosine to determine the components produces the following sequence of numbers. Once you have these numbers on paper, you've really achieved the halfway point, if not more than the halfway point, in this question. So in this case, we have two components, totals, which are negative. So this is negative, indicating that we're going to be going west, and this one's negative, indicating that we're going to go south. So when we draw the diagram, we're going to draw it this way and this way. And that'll be 28,721. Now I'm rounding it a little bit here just because the answer is to 3 significant digits, and we have 5 significant digits here. So we're more than fine with just using the accuracy that I'm presenting. What's really important here is that you don't get lazy here with the accuracy. Like over here, I went overkill. What was that? Not 8 significant digits. Okay, that's a lot of significant digits of accuracy. You could get away with like 4 or 5. Now over here, let's get that total. So that'll be F. Let's try that arrow again. So that's f, and that's theta. So using the Pythagorean theorem and the inverse tangent, we find that f and theta are as follows. And that allows us to complete the question because we have the magnitude and we have a means for identifying the direction of the resultant vector. So this is our last one, so I'll type it up nice. So this is going to be 39,500 pounds with a direction of 43.3 degrees south of west. And there you have it. Hopefully you've gotten used to the process, because the next booklet I'll be going through this process at a more steady pace than what you've been seeing. Definitely at par, at least, with the pace that I'm doing here. What you might see with me in future classes where I do this component method, I probably will fill the table in at the same pace that you're seeing, but this stuff over here and this triangle over here, I might not draw it every time. I might just tell you the two numbers here. So if I don't write this in the future, it's because we've done so many of them already that we need to move on to something more high level. So what you'll see with me in the future is most likely the table, these two numbers, and then the resultant vector, its final answer. And that's about it. So that, hopefully you had fun today, and you're not too bogged down with your other commitments. Especially, I heard that you have a lot of things due.